something called the second derivative test to determine local extrema. And it's supposed to be kind of like a faster way than doing the increasing decreasing. Today on your homework it says find local extrema using the second derivative test. But after today, like, I don't care how you find local extrema. Like, I'll never say you have to do the second derivative test, you have to do the first derivative test. You just need to know that both of them are options and do one of them. Most of the time we tend to go back to the first derivative test, but you never know. Maybe you'll like the second derivative test better. Sometimes the second derivative is terrible option. I just like to do the first derivative test. But here we go. Second derivative test. If f is a function such that the derivative equals 0, or is undefined, I probably should say, and the second derivative exists, containing that value, instead of plugging into the first derivative, we can think about concave up and concave down, which Philip was kind of hinting at yesterday when we talked about this. If you take your critical point, right, where the first derivative equals 0, and you plug it into the second derivative, and you get a positive number, that means on that part of the graph, if the second derivative is positive, that means that it's concave up, right? So if it's a possible turning point, and when you plug it into the second derivative and you get concave up, do you agree that that has to be a relative minimum? So I draw the picture a lot because it helps me to think about concave up. Oh, that would be a minimum. So instead of having to plug it into the first derivative, you just plug in the second derivative and you see whether it's positive or negative. If you plug your critical point into the second derivative and you get a negative number, that's implying that at that critical point it's concave down, which means if it's concave down at that possible turning point, then that would be a relative maximum. Here's why we tend to kind of go back to the first derivative test a lot. Because sometimes you plug that critical point into the second derivative and you get that it equals 0. That doesn't tell me anything. And so that means the test fails and you still have to go back and check it in the first derivative test. And so that's where you might say, this is stupid, why do you even show me this? Because I might have to end up doing the first derivative test anyway. And I agree. The other reason I wouldn't use the second derivative test is because what if your second derivative involves like the quotient rule and this awful stuff? Why would you want to do that when you could just go back to the first derivative? And so that's why I want to show you this. We'll talk about it, but I'm okay if you just stick with the first derivative test for the most part. All right, but it is kind of cool on some of these problems, especially like these lovely polynomials. I believe you have 3 or 4 problems on your homework today. The directions say find all relative extrema using the second derivative test. So we still have to do the first derivative. We still have to find our critical points. But then instead of checking them on the number line to see what's happening on either side of it, we're going to plug them in the second derivative. I'll show you how that works. So let's just do our first derivative. So I get 3x squared minus 12. And I'm going to go ahead and find my critical points. So I add 12 over and divide by 3. And I get x equals plus or minus 2. Questions on where I'm getting at? So you could still make your number line, plug it in, see what's happening on either side of 2. Or we could do the second derivative. If I take the second derivative, very simple on this one, would just be 6x. Instead of making my number line and having to plug stuff in and seeing whether it's positive or negative, I can just take my critical points and plug them into the second derivative and think about whether that would be concave up or concave down, because that would tell me whether it's a max or a min. So if I plug negative 2 into my second derivative, I'm going to get negative 12. That is a negative number, which means concave down, which means I can say that negative 2 is a relative max. And if I plug 2 in there, I get 6 times 2, which is 12, or you could just say positive there if you want. Positive number means concave up, which means I can say that is a relative min. Does the idea of the second derivative test make sense? You can see where this could get really ugly, because if the second derivative was terrible to find, it's not even worth doing, I think. But like on a problem like this, I don't know, is it any faster than doing the first derivative test? I don't know. You still got to find it and plug the stuff in. If I want you to find all the relative extrema points, remember that I'm not finished yet here. And again, I tend to not actually even write these numbers. Like I would write negative here and positive here, because I don't want to get confused and think these are the y values that go with it, right? These are just the second derivative values. into the original problem to get that value. And again, it's okay to use a calculator, but just be aware that most of the problems that you see on your next test are going to be without a calculator, which means I expect that you can plug values into something like this and get me the answer without using your calculator, with just arithmetic, that would be -8 plus 24 minus 5. Is that 11? And on the bottom would be 8 minus 24 minus 5, which would be -21. Same answers you would have got doing the first derivative test, and again, on your test for this chapter, I won't make you do one or the other. Only today do I make you do that. Let's do E1, that's our favorite, right? I have a big mess going on over here, as usual in my life. If you want, there's a bunch of answer keys here that should have folders that they go in somewhere. So you can find the folder of the answer keys. Product rule, yes? So that would be 1 times e to the negative x. Leave the x alone, and the derivative of e to the negative x would be e to the negative x times the derivative of negative x, which would be -1. So is it okay if I just write that as e to the negative x minus x e to the negative x? And again, we could go ahead and find the second derivative, but for me, if I'm finding local extreme points, once I find the derivative, I'm going to go ahead and find my critical points, and then we can do the second derivative. So just like the one that we just did on the board, even though there's an e in here, if I'm trying to set this equal to 0, I can factor that e to the negative x out, and I'm left with 1 minus x. And again, really super great when we're trying to find something equal to 0. This is never going to equal 0, so I can just disregard it, basically. Doesn't work. And then I can say 1 minus x equals 0, so x equals 1 is my critical point. For me, I think the second derivative test is silly on this problem, because I could just make my line, I'm only checking one number, not that big a deal to do the first derivative test. I'm going to do the second derivative test just to show you, but again, I don't know, I shouldn't tell you I'm not a big fan of it, but I'm just not a big fan of the second derivative test. But to do the second derivative test, now I have to take the second derivative. So I could either do the product rule here, or I could just go back here and do the derivative and then do the product rule again. Either way, I have to do the product rule, so have you done it yet? Do you want to go back to this or go to the factor rule? It doesn't matter, we're going to get the same answer. I'll just go here. If I take the derivative of e to the negative x, it's going to be negative e to the negative x. Minus derivative of x is 1, so then that's just going to be e to the negative x. And then when I leave the x alone, the derivative of e to the negative x is going to be negative e to the negative x again, right? But since there's already a negative out front, does that change to a plus? Right? Are you following on that? Because that negative is still there, so the two negatives work out. You could actually put these together, they're the same. You could say that's negative 2e to the negative x plus xe to the negative x. I could factor out that e to the negative x and get negative 2 plus x. If I was trying to find inflection points, second derivative test isn't such a bad idea because you already had to find the second derivative and then you could plug your stuff in. But when the second derivative is complicated, that's when I'm not, like, I just feel like I could have been done with this problem already. But now I can plug 1 in here. Is that going to be a negative answer or a positive answer? 2 plus 1 is negative, which means that's going to give me a negative answer, which means it's concave down. So I can say that there is a relative max at x equals 1. And to find the y value that goes with it, I have to plug it back into the original problem. See why I'm on the fence about the second derivative test? Usually when we review for the AP exam and I review all the tests, the first derivative test, the second derivative test, usually someone says, why do we even need the second derivative test? You don't. You can do it with the first derivative test. But if I plug 1 back in there, that would just be e to the negative 1, or you can write that as 1 over e. Both are acceptable answers to get your problems there. So like I said, there's a few questions on your homework that say do the second derivative test. The other stuff on your homework is concerning maybe a little bit more with the velocity acceleration stuff, and also just talking about looking at graphs and being able to tell me things about the function, or giving you some information and asking you to write a graph given some information about the derivatives. So I drew these lovely graphs for you. And I said, tell me the signs of the first and second derivative. And notice I did problems that it's going to be the same on the whole graph. But just thinking about, if this is the original function, what do you know about the first derivative? What do you know about the second derivative? Because we've got to start thinking about, what does the first derivative tell me? What does the second derivative tell me? So what does the first derivative, what do I know about the first derivative from this graph? Because this graph is decreasing the whole time, yes? And decreasing graphs mean a negative first derivative. So I can say the first derivative is less than 0 on that entire graph. What can you tell me about the second derivative? Because that is the definition of concavity. But yeah, it's concave down, right? Philip says because the first derivative is negative, then he knows the second derivative is negative there. But it's concave down. Like, you should be able to see that all of our tangent lines would be above there. And so it doesn't ever change concavity, so it's always less than 0. The last few years on the AP exam, on a multiple choice question, there's been a problem where they, I don't remember if they give you an equation or they give you a graph, and they ask you to compare the actual value of the function to the first derivative to the second derivative, and they're making you think about increasing and decreasing and concavity, and it's definitely a hard question, I think, when you're doing it. What about this one? What about the first derivative? Because the first derivative is greater than 0, right? Because it's increasing. Do you agree with that graph? Going up. Think about, like, we could actually write the equation for this if we had a line there. But this is definitely a linear equation, right? Like, it's something x to the first power. So when we took the derivative of that, because it has a positive slope, it's just going to be a positive number. It's always positive. What would happen if we took the second derivative? What would we get? We would get 0, which means the second derivative actually equals 0, because does this graph have any concavity? It doesn't. It's not concave up or concave down. It's linear, and so that was kind of a little tricky problem there. What time did we get out here today? Oh, wait. I want to skip this next one, making the connections, and we'll start there tomorrow, because I want to actually think about it with you instead of just telling you what to fill in those blanks. So we'll come back to this because it's a very important page, but let's look at this last one because there's one on your homework like this. And it says, sketch a smooth curve y equals f of x through the origin with properties that the first derivative is less than 0 for x is less than 0, and the first derivative is greater than 0 for x is greater than 0. And so when they give you a problem like this, you need to make sure you read what they tell you. Like, right away I see it goes to the origin, so there's a point at the origin. Like, you know that's part of your graph. And then you just have to make sense of what it says. They can talk about the first and second derivative now, because we know what that means when they talk about the first and second derivative being positive or negative. There's really more than one right answer, but there's definitely, like, you don't have to overthink this. There's no, like, you don't have to do a fancy answer. If the first derivative is less than 0 when x is less than 0, telling me on this side of my graph? It's decreasing, right? It's going down over time. The first derivative is less than 0 means the function itself is decreasing. So I need to show that this is decreasing on this side. So could I just draw on something like that? I know it goes through the origin, so that's why I had to make it go there. And then, when x is greater than 0, I know that the first derivative is greater than 0. What does that tell me about my function? It's increasing. So could I just draw something like that? That meets the requirements of that. So don't overthink these problems. Not supposed to be tricky, just supposed to be make sure you met the requirements of what it's saying to do on those problems. There's one on your homework like that you have to draw something in. It said a smooth curve. That's how I knew not to make like a sharp corner, like an absolute value graph. Wouldn't fit that because it's not a smooth curve. Okay? So we'll come back to that other page. We'll start tomorrow with that. But this is 4-3, day 3. The plan is that we'll do a worksheet tomorrow, but we'll start with finishing up those notes first. And then I think I'd like to review Thursday and then make your review due Friday so we can go through it. And then test Monday. Well, if we have the test Monday, then Tuesday I'll probably, you'll do test corrections. So I have an AP conference Tuesday, so I'm not going to be here. So, so I think that'll be the plan and it'll work out all right. And plus it'll give us time to review. Friday. Yes, yes. Cause I know you're going to be at an international festival. There's a couple of you. There's only 2 of you, I think, that were on the list. But yes.